Okay, hi everyone. Welcome to the first lecture. So I'm going to be doing a series of these lectures. So every week there'll be a couple lectures where I'm going through my notes here. The notes will be posted on Canvas, and I'll have like filled in versions of my notes as well for you to follow along with. So I encourage you to follow along. Sometimes I'm going to say like try something on your own. When I say that, you can take a minute. I'll pause for a second. You can take a minute to try it on your own. Pause the video. I'll just go ahead and fill in an answer after I talk about that. So today we're going to talk about 4.1, so antiderivatives. So in Calc 1, the whole point of the course was doing lots and lots of derivatives. And in Calc 2, we're going to be going backwards. So we already know about derivatives, and we're going to be learning about this process for sort of reversing derivatives. This class is integral calculus, so we'll see pretty soon that a lot of what it means to do an integral is kind of reversing a derivative. So today we're going to talk a little bit about that. I'm just doing some simple examples, and then talking a little bit about this application. I'm thinking about velocity and position and what it has to do with derivatives. So let's just maybe start with a few examples, kind of warm up. Just maybe recall from Calc 1, we learned all these different rules for finding different derivatives. So we'd write it like this, right? d dx of something. So I'm going to take the derivative of this expression. Here I'm going to do the derivative of this expression. And the d dx is just kind of reminding us that x is the variable here. And we just have a couple of rules that we learned, right? We learned some basic rules. So for example, x squared, you might remember this is going to be 2x, so sort of the 2 comes down in front, and plus 1. So we learned rules about if I have x to the something, so like if I have x squared, the derivative turns into 2x. If I have x cubed, the derivative turns it into 3x squared. So this is the original, this is the derivative. And we learned a bunch of other rules, but this is one of our most important ones, maybe called the power rule, because there's a power on the x, and our general pattern was the power on the x sort of comes down in front, and it goes down by 1. So like here the 3 turns into a 2, here the 4 turns into a 3, and that was our rule. We could kind of write this generally as x to the n goes to n times x to the n minus 1. If you want to write it sort of for short, the n just means any number. So if I have x to the 101, it'll turn into that same number comes out in front, and then times the number subtracted by 1, so x to the 100. So we learned a bunch of derivative rules. This one is called power rule, and I'll summarize some of the rules on the next page. So that's for something like x squared. We also learned that when you're taking the derivative of an expression that's like something plus something else, the derivative just goes through. So we do the derivative of the first part plus the derivative of the second part. So like here, the derivative of x squared is 2x. The derivative of x is just 1. And so the derivative of this sum, x squared plus x, is the derivative of the first thing plus the derivative of the second thing. So that might seem sort of simple, like obvious, because we've done that a lot, but I just want to emphasize that it really matters that it's plus here, right? If I just did like x squared times x or something like that, and I told you to do the derivative, I can't do, it's not going to be like 2x times 1. I don't do the derivative of each part separately and multiply them. That doing it separately only works if it's plus specifically, or minus, but not times or divides. When you do have to multiply, take the derivative of two things multiplied together, there's a special rule we learned for that. You might remember you have to use something called the product rule. So there's like a special rule for multiplying, for taking the derivative of products of two functions. Or product just means times, right? So there was like this kind of generic format you might remember. There was like, if I have f times g, so f and g are functions, and I do the derivative. So remember this little tick mark is, we read it as prime, f times g prime, and that's just another name for taking the derivative, just another notation. I'm going to be using both notations, so I'll write this one here. So like, I could have written like ddx of f times g, the same thing. So the derivative of f times g, our rule is I do f's derivative times the original function g plus the original function f times the derivative of g. So there's a little like thing where you do the first one and then keep the second one and then add first one, do the derivative of the second one. So let's see how that works over here. So I want the derivative of, I'm going to kind of think of this as 5t squared times sine of t. So that's like sort of my f and my g, my two parts. There's f and there's g. So I want to do the derivatives of each part. So, you know, if I wanted to, I could go over here and kind of write what f prime is, what g prime is, and then kind of put everything together. Let's go ahead and do that for the first one. But usually you can kind of do this sort of like writing as you go instead of having to write on the side. But it's fine to write over here. So let's look at f first. F is 5t squared. So we already know the derivative of t squared is like this example over here, right? X squared goes to 2x. If the variable name is t, that's fine. Same thing. T squared is going to go to 2t. So this 5t squared, the t squared part becomes 2t, but then we have this 5. So another rule we learned about derivatives is that if you're doing the derivative of like a number times your function, then you just keep the number and then do the derivative. So up here, I said you can't just do the derivative of each part when you're multiplying. You have to use the product rule. That's sort of specifically when you're multiplying two functions, like two things with x's in them. But if I'm multiplying a number times my function, I actually can just sort of keep it. So, for example, if I'm doing the derivative with respect to x of, say, 5 times x, then I know the derivative of x is 1, and I actually just keep the 5 there. So I keep the number, and then I times by the derivative of x. So like x goes to 1, so I'm going to have 5 times 1 right here. So you can kind of think of it as like the ddx sort of symbol sort of moves past the 5 and goes on to sort of just the x part, if that makes sense. That's one way to think about it. You like pull the 5 out. So same thing's going to happen here. I have 5 times t squared. So the 5 just stays. And then I just do the derivative of t squared. So it's times 2t. So that's, I might as well simplify as I go. That's 10t. There we go. That's f prime. So remember, backing up, we're trying to do the derivative of this product, f times g. So I need to do f prime times g, f times g prime. So I need my f prime, g prime. So here's f prime. And then for g prime, g is sine of t. So we learned these other rules about taking the derivative of trig stuff. So sine becomes cosine of t. So in addition to the power rule and the product, so here's kind of maybe boxing some of the rules we learned. We got power rule, we got product rule. There's also trig stuff. So the most important one is that sine goes to cosine. There's other ones, right? Cosine goes to negative sine. And because of this, leaving the 5 out front idea that we did before, that already tells me right away, actually, that negative sine, right? Negative sine is like negative 1 times sine. Right, think of this as negative 1 times sine. I already know that sine goes to cosine, and the negative 1 just stays out front, just like the 5 stayed out front. So negative sine goes to negative 1 times whatever sine goes to. Sine, we already know, goes to cosine from this first line. So it'll be negative 1 times cosine, otherwise known as negative cosine. I'll just write the last one just for completeness. Negative cosine goes to negative sine. It goes back to positive sine. Sort of the same rule. I already know that cosine itself goes to negative sine from line number 2 here. And so negative of that goes to positive sine. Okay, so there's a bunch of these rules. We have to review some of them as we go. But for this, we know sine goes to cosine. That's all we need. Okay, so we just got to assemble this together. So the derivative of f times g, f prime times g. So my f prime is 10t. So it'll be 10t times sine, so the original g, sine of t. And then plus, right, f times g prime. The original f was 5t squared. And then g prime is cosine. Right, so remember this f and g is just like standing for whatever function's there. Okay, so I spent like some extra time on that, just making sure every little step made sense. In general, I'm going to go sort of, like if you felt like that was a little bit slow, like if you feel pretty good about this derivative stuff, that's totally fine. I'm going to take my time in these videos just to make sure that everything's explained, if there's stuff you're not sure about. But if you ever feel good about something that I'm talking about and you want to fast forward a little bit, that's totally fine. I'm going to try to take my time when we do these. Okay. So, yeah, so that's our warm-up. We just kind of remembering a bunch of derivative rules from last term, or 251. Okay, so that's sort of derivatives. There's some other rules, right? There's quotient rule, this chain rule. We'll kind of see more, remember more of these as we go, but these are some of our basic ones. Okay, so I promised that we were going to talk about antiderivatives. So it's basically going to be anti-derivatives, so doing the derivatives backwards. Meaning, instead of starting with a function and doing its derivative, starting with the derivative of a function and trying to figure out what the original function was. So here's maybe a place you can pause and think about this for a second. I'll say an answer in a minute. Can you find a function whose derivative happens to be this guy, 2x plus 1? So some mystery function that when I do this derivative thing, I end up with 2x plus 1. So maybe pause and think about that for a minute. Okay, so really we want to think about these power rules, right? when I'm looking at this, I want to think of, are there any derivative rules I know of which result in something like this? We've already seen a couple on this page, right? I know, maybe looking up here, that if I had an x squared, it's going to go to 2x. Which means that if I have something whose derivative is 2x, I must have started with x squared. Or at least that's one thing you could have started with. Remember, because of the plus, the derivative goes through the plus, right? I do the derivative of each part. So I just have to separately think of something whose antiderivative, separately think of something whose derivative goes to 1. Derivative is 1. And we kind of saw earlier, like, that x goes to 1. Like here, this derivative of x goes to 1. I noticed I didn't actually have that one on my list of power rules over here, so I'll just include it. X by itself goes to 1. You could think of it like this one. If you imagine n is 1, right? Because you could secretly imagine an x to the 1 right there. I'll let you think through that, what would happen if n is 1. Okay, so coming back here, so 2x must have come from, right? Must have come from x squared. 1 must have come from x. And because it's plus, I must have started with x squared plus x. By the way, this should not be surprising. This is literally the example we started with. So if you just spotted that earlier on the page, that's also good. But we can think about taking each term and going backwards. So if I had just given you this, you could come up with this x squared plus x. Okay. here I say, what about 5t squared cosine t plus 10t sine t? So maybe think about that for a second. So we, just like the previous example, we did this one already, right? We saw that when I did my power rule, we ended up with this on the right-hand side. So we must have started with this over here. So something whose derivative is this guy. Okay, cool. Okay, so I'm going to scroll down a little bit. One more example here. What about 1 over 2y? So this is not one that we did already, and it's a little trickier. But let's just follow this hint. It says try taking the derivative of log 2y. Remember, this ln means natural log, logarithm. So think about that for a minute. Try it on your own. So if we follow the hint here, so I have log of 2y. So I'm going to try to take the derivative of that. So maybe I don't know what I'm doing yet. I'm just following the hint, and that's okay. By the way, remember the d notation, d dy, that's fine. That's another way of saying derivative. It's y instead of x. That's okay. Just means y is like the name of the variable in my function. So another derivative rule we might remember is what happens to ln. So ln x goes to 1 over x. That's the derivative. And here it's ln of something. So we have to remember how do I do the derivative of one function like inside another function? So that's another rule that we mentioned but didn't talk about, is the chain rule. So it's usually written like this. So if I have f of g of x, and I want to take its whole derivative, I have to do the derivative of f, and then I plug in g, and then I multiply by the derivative of g. So let's just unpack that a little bit, right? What do I even mean, f of g of x? Well, that's exactly a situation like this, where I have a function that's sort of inside another function. So log of 2y is an example. I have sine of x squared. Or I could do, x plus 1 squared. Here the sort of outside function is something squared, and the inside function is x plus 1. So like here I could say f of x is x squared, meaning like something, black box, something squared, being the outside function. And the inside function would be x plus 1. And when I write something like f of g of x, right, what does that mean? It's f of whatever g of x is. G of x in this example is x plus 1. So it's f of x plus 1. F of x plus 1 means, whatever you're plugging into f, square it, right? F of 2 is 2 squared. F of 10 is 10 squared. F of x plus 1 is x plus 1 squared. So I take x plus 1, that's my input, and I square it. So here I had x plus 1 squared, and I kind of thought of it as an inside function, x plus 1, and like this outside function, x squared. Sometimes it's hard to think of like what's the inside and the outside, but a lot of times it's sort of straightforward. So like with sine of x squared, sine is like the outside, sine of x is like the outside function, and x squared is the inside. And over here, log of x, log of something, is the inside function, or the outside function, and 2y is the inside. So the chain rule is telling us how to take the derivative of a nested function like that. And the rule is that we take the derivative of the outside function and leave, right, this g of x just like stays, like the x plus 1 would stay. And then we also have to multiply by the derivative of the inside function. So let's just see what that looks like here. I know log goes to 1 over right? Log of x goes to 1 over x. So I should think of that as log of something goes to 1 over something. That something is kind of like a black box. Log of something, its derivative is going to be 1 over that something, basically, except for the chain rule, right? So I'm going to have 1 over the inside, that's 2y. So that's, that 1 over 2y is like this part, right? I did f prime, sort of 1 over x, but then I plugged in my inside function, which was 2y. So this 1 over, this kind of should be 1 over x, but the inside function was 2y, so it's 1 over 2y instead. I'm putting that 2y wherever the x would be. So that's that first part, and then we have to do the second part, which is multiply by something, multiply by g prime. So g is 2y, right? This is, I should have labeled this. This is g. So I got to do the derivative of 2y. That's like power rule from before. The derivative will just be 2. So I'll have times 2 here. Okay. So that's my derivative of log of 2y. Why is that a good hint? Well, if I simplify this, remember I have 2 times 2 is going to cancel with the 2 that's on the bottom. So I'll just have 1 over y. So, right, we're trying to find a function whose derivative ends up being 1 over 2y. We found a function whose derivative ends up being 1 over y. Right, we learned that log of 2y's derivative is 1 over y. So that's a function whose derivative is 1 over y. So if I wanted to have the end result be 1 over 2y instead, that would just mean I have to change the starting thing a little bit. So maybe think about that for a second. How could I change my original function in order to actually end up with 1 over 2y in the end? So what you can do is, because we learned this derivative rule up here, where if there's a number out front, that just stays when you do the derivative. That's also true if you have a fraction, because like I could have x over 2. Let's say x squared over 2. The x squared becomes 2x. That just like stays in the top. And the 2 is just going to stay. The 2 is a number just like the 5. Maybe to make that a little more clear, remember I can always think of like x squared over 2 is the same thing as 1/2 times x squared. So this is a really good algebra thing to be able to do. Just something over a number is always 1 over that number times a something. So this 1/2 is a number just like the 5 is. So when I do the derivative, the 1/2 just stays. And I'll multiply by whatever the derivative of x squared is, which is 2x. And then, like, these are the same too, right? 1/2 times something is the same as that something divided by 2. That's a good fraction algebra thing to be comfortable with. In the end, in this example, you just get x because those 2's will cancel. Okay, so coming back to our log example, right? If I want a 2 to end up on the bottom in the end, I should have just had a 2 in the bottom at the beginning because it's just going to stay there. So if I just change my original function to be this log 2y divided by 2, then what happens? Well, this divided by 2, remember I can think of that as a times 1/2, and so I'm just going to keep a times 1/2 out in front. And when I do the rest of the derivative, that just is this part, which stays there. These, like this, maybe you could think of this 2 and this 2 canceling, and there's the 2y left in the bottom. Or if you like, this 2 cancels with the, sorry. You could say these 2's cancel, and there's the other 2 left, and you have 2y. Okay, so that example was a little bit involved. So it's not always super simple to think of a function whose derivative is a given function. We will learn a bunch of tricks for doing this, which make it easier, but you can try to think through specific examples even without those tricks. Definitely tricky though. Okay, so just a little vocab here. All this we've been doing is thinking of a function whose derivative happens to be some particular function. So the word that we're going to use is antiderivative. So if I have two functions, I'm just calling them little f and big F. If I happen to have that the derivative of one function is the other one, so the derivative of big F is little f, then I call big F an antiderivative of f. So little f is the derivative of big F is the antiderivative of little f. So a lot of this class we're going to be finding antiderivatives, and I'll just use this language, find an antiderivative, and I mean do this process we've been doing. So for these next couple, I've labeled them as you try. So I encourage you to pause here and just try to do these on your own. Some of them need a little bit of remembering how some of our algebra derivative tricks. And some of them are, you have to remember some specific derivatives that we learned about. So I think I'm just going to not talk through these too much, but kind of write the answers down so you can check after you've tried them. So try them for a minute. Okay, so for the antiderivatives, you should be getting, so my antiderivative, if I wanted to, I could write big F, but I'll just leave it. Antiderivative is going to be 3x cubed over 3 plus 2x squared over 2. So let's see how I got that. Right, x squared, I have to do my power rule sort of backwards, right? I know that like x cubed goes to 3x squared, for example, when I do the derivative. So what's happening is like the 3 goes in front and I decrease the power by 1. So doing it backwards means I'm going to increase the power by 1, and well, I originally was multiplying by 3, so I'll probably have to divide by 3 to go backwards. So that's we'll talk about that more in a minute, but that's like a good shortcut, right? This x squared, when I take its antiderivative, I'm going to get x cubed over 3. And I can just check that it works, right? If I take the derivative, so this is a little confusing. I'm going to say anti right here. If I take its derivative, I should get x squared back to start with. The 3 comes out front and goes down to 2. That's what happens in the top of the fraction. And just like we said above, the bottom of the fraction just stays there because it's a number. These 3's cancel, which is the whole point. I'll have just x squared left over. So that's a general like rule for antiderivatives. If I have like, maybe I'll write over here. If I have x to the n, the antiderivative is going to be x to the n plus 1 divided by n plus 1. So that's like kind of abstract with the n's, but what I mean is like if I have x to the 5 and I do the antiderivative, it'll turn into x to the 6. So I just plus 1, and then I divide by the new number, 6. So this is like a big deal. We're going to be doing this like all the time. Like every day in this class, you're going to have to do, every day in this class, you're going to be thinking about these kinds of derivatives. So like every single problem basically is going to have these. So make sure to do a couple examples and make sure they make sense. You know, x to the 7 is going to go to x to the 8 over 8. I'll just mention now, it still works even if it's not whole numbers. So if I have x to the 1/2, for example, I add 1 to the top, to the exponent. So if I don't want to think about adding fractions, I can even just write 1/2 plus 1, just like for the moment. And I divide by the new exponent, whatever that is. Okay, so 1/2 plus 1. So this definitely looks a little awkward right now, but that's, even if you don't like simplify the fractions, that's technically correct, right? It's 1/2 plus 1, whatever that is, divided by that new exponent, whatever that is. We should be able to like do that in our head though, or at least simplify, right? So 1/2 plus 1 right? That's 1/2 plus 2/2, otherwise known as 3/2. So that's a really common one. A 1/2 will go to a 3/2. So if I simplify this, I'll have x to the 3/2, and my denominator is the same. It always matches the new exponent. By the way, another fraction rule. Whenever I have a fraction in the bottom of a fraction, that's the same as having that fraction out front, or on the left or on the right, same thing, but flipped over. So it's pretty common to write it this way too. You can kind of think of the 3 as like staying in the bottom, and then the 2, it's like 1/2, like I'm dividing by 1/2, which is the same as timesing by 2. So this fraction flips. One more just example of maybe that's a little weird. If I have x to the, say, -2, this rule actually also works. So I do x to the -2 plus 1, whatever that is, and then I have -2 plus 1 in the bottom, whatever that is. So again, even if I haven't like simplified it yet, that's correct. I can add 1 to the exponent and add 1 to the, or have the denominator be that new exponent. Okay, so this becomes x to the -1, right? Divided by -1. Another good fraction rule. If I divide by -1, it's the same as multiplying by -1. So this is the same as -1 times the top, which is the same as just negative the top. So I can write negative x to the -1. So we'll use these a lot as well. I'll just say this right now. X to the 1/2, we use that all the time because that's another way of writing square root of x. So a lot of times I'm going to be doing like the derivative or the antiderivative of x of square root of x, and the easiest way to do it is to just turn it into x to the 1/2. That's just rewriting it. This 1/2 exponent is just another way of writing square root of x. They're the same thing. So I can do the derivative or antiderivative by turning it into that and then doing my power rule. Same thing with x to the -1 is another way of writing 1 over x. So if I ever want to do the derivative of 1 over x, I'll just rewrite it as x to the -1 and then do my normal power rule. You could also have like x squared in the bottom, and that's x to the -2. Right, there's secretly like a 1 right here. So those are actually super common, and you're even going to have situations like 1 over square root of x, for example. How do I do the derivative of that? Well, first let's change it into 1 over x to the 1/2, because square root just means to the 1/2. But now it's a number, it's x to the something in the bottom, right? Like here, x to the 2 was in the bottom, and that just becomes that same exponent, but with a minus sign in the top. So this is x to the -1/2. So we're really going to be really important, like for the whole course, we're going to be like given problems where it's like written like this, and I want to turn it into this exponent form to make it easier to work with. Okay, I know I talked a lot about just that one problem, but there's a lot of good things to review. So let's take a look at 2, 3, and 4. So for g, negative cosine, I kind of basically just have to reference the trig rules that we mentioned above. I know that the derivative of sine is cosine, so the antiderivative of cosine better be sine. So the antiderivative of negative cosine better be negative sine. So not too much to say there, just double check the trig rules and make sure it makes sense to have the -1 out front. Let's look at this one. Okay, so this is a great example of having a root in the bottom. So let's transform this into the different exponent version to make it easier to look at. First thing I'm going to do is pull the 1/2 out. So what do I mean? Remember, 2 in the bottom is the same as 1/2 out front. So I'll have 1/2 times the rest of it, 1 over square root of x. So that's just going to make things a little easier. I can keep the 1/2. Root x is just x to the 1/2. And x to the power in the bottom is the same as having x to that negative power in the top. So x to the negative 1/2. And now I'm all set to do a power rule. So because I'm doing an antiderivative, I want to do sort of reverse power rule. So that's this thing we were talking about up here. I guess I should label that. Maybe call it reverse power rule. I'll probably just call it power rule. So, but like for antiderivatives. So we got to add 1 to the exponent. So negative 1/2 plus 1 is 1/2. And then I'll divide by the new exponent. This 1/2 just stays because it was just a number out front. Cool. I can simplify that. The 1/2 on the bottom is the same as 2 out front. I kind of flip the fraction. I said whenever there's a fraction in the bottom, it's the same as flipping the fraction, but it's in the front. So flipping 1 over 2 means 2 over 1. I still have the other 1/2 sitting there, and I have x to the 1/2 here. These will cancel. You'll just have 1 times x to the 1/2, which I can write as square root of x. So the antiderivative of this thing is square root of x. If we had done the derivative of square root of x previously, we would have maybe seen that it turned out to be this guy. Okay. One more. So this function here, k of x, is 1 over 1 plus x squared. So this is one that's pretty hard to do if all you have to work with is power rule and what we've talked about so far. We just have to kind of know, just from knowing, that there is a particular function whose derivative happens to be this guy. So this antiderivative is arctan of x. So this is not something you'd know just by looking at it unless you happened to remember that arctan was a function that we learned the derivative of, and its derivative happened to be 1 over 1 plus x squared. So it's kind of annoying because it just seems like out of the blue. But it just turns out that like the sine stuff and the cosine stuff and like tangent and arctan, that's like common enough that this like chunk of algebra shows up pretty often, and we're going to want to learn to recognize it as the derivative of arctan, meaning its antiderivative is arctan. Remember, arctan is like the inverse trig function for tangent. You can let me know if you have questions about that. We'll use it a little bit. But the main point of this example is sometimes there are sort of complex looking things that just happen to be derivatives of functions we know already. And even if it seems a little kind of random, that's fine. That, we can find the antiderivative of this thing just by knowing that it came from being the derivative of a particular function. So kind of maybe summarizing a lot of what we just did. Here is sort of a list of a bunch of derivatives that you already know about, right? If you know your derivatives, you already know a bunch of antiderivatives for free, right? I know the derivative of x is 1, which means the antiderivative, right? If I go backwards, that's the antiderivative. The antiderivative of 1 is x. I know the derivative of x squared is 2x, so the antiderivative of 2x is x squared. And we mentioned this earlier, power rule. So I can do the antiderivative by going backwards. I'll just kind of list a couple of these. I basically did this earlier. Sine goes to cosine. Cosine goes to negative sine. Derivative of tangent. So it's secant squared. That's something we learned in 251. If you have it memorized, great. You can figure it out if you forget, because tangent is sine over cosine, and you can do quotient rule, like the derivative of this. But it's probably good just to kind of know it off the top of your head. We'll use it a lot. And just for some completion, same idea. You might remember the derivative of secant happens to be secant times tangent. Again, you can show it because secant is 1 over cosine. So you can do quotient rule on this. I won't go through that, but if you want to practice quotient rule, that's a good exercise. And then here's ones that you can show the same way. They'll come up sometimes, but not super often. As I mentioned about arctan, we learned in 251 the derivative of arctan is this. Derivative of arcsine is this. So they're kind of just like weird chunks of algebra, but sometimes we'll be asking about like what's the antiderivative of something that looks like this, and we're supposed to just know it's arcsine. It's not like algebra you're doing. You're just like knowing that it came from a particular function. There won't be too many of those, but it happens sometimes. Okay, so we have all these derivatives from regular calculus. We can go backwards to find antiderivatives. Okay, I want to talk about why we would care about antiderivatives in just a second. I do have to mention something really quick first. So maybe pause and think about this. How many functions can you think of with this particular derivative? Right, we found one derivative of this function earlier, right? We figured out that x squared plus x was the derivative of that function. I'm wondering, can you think of any other ones? Like, is that the only one that you can imagine? So let's think about that. Okay, so are there other functions whose derivative is that? Well, yeah. I could do x squared plus x plus 100. Right? What's the derivative of this? Well, power rule says x squared becomes 2x. X becomes 1. And what's the derivative of a number? Just 0. So this is just 2x plus 1. So we found another function whose derivative happens to be 2x plus 1. And since the derivative of any number is 0, this doesn't have to be 100, right? It could be 101. Or, whatever. Any number you could put here is going to be something whose derivative is 0. So actually there's an infinite number of functions whose derivative happens to be 2x plus 1. At the very least, I can make a new one just by changing the number here. So that's important. I'll mention this here. If you have the derivative of something, if little f is the derivative of big F, then little f is also the derivative of big F plus c for any constant c. So that just means, my original function plus anything, any number, is another antiderivative. So that's a little bit annoying, and we'll have to deal with this a little bit. But what's maybe surprising is that that's actually the only thing that can go wrong. So this is not obvious at all, but it turns out that, yeah, I can find a different antiderivative by changing the number, but actually that's the only thing I can do. There's no, it turns out there's no other, random function, that I could try to write down some random function. No matter what you write down, there's no function whose derivative is this, except for our thing we found before, x squared plus x, and then maybe plus some constant. So a constant is the only difference between different antiderivatives of the same function. So that's not obvious. You need to prove that. We might prove it or talk about proving it later, but for now, just to kind of take it as a rule. An antiderivative is the antiderivative plus maybe a number. So we usually say that big F plus c is the antiderivative. So for example, I know that 2x is the derivative of x squared. It's also the derivative of x squared plus 100, right? So I have two functions whose derivative is x squared, or whose derivative is 2x. X squared goes to 2x. and x squared plus 100 also goes to 2x. So I will say that x squared plus c is the antiderivative of 2x. Right, this one is x squared is an antiderivative, like it's one of them. X squared plus 100 is another an antiderivative. But I'm going to capture all the possible antiderivatives by having this plus c. So I get to say x squared plus c is the antiderivative. So every antiderivative of 2x is contained in this expression. Just pick different c's. So x squared plus 7 is another one. Okay, so it's kind of a minor point to say the antiderivative versus a antiderivative, but the plus c thing will come up several times, so got to mention it now. Yeah, so I say you try, find the antiderivative of each function. The main thing is to find an antiderivative and recognize you're writing plus c. I'll go ahead and mention here e to the x, because I don't think I mentioned it yet. Another derivative rule. E to the x, its derivative is just e to the x. So that's kind of the cool thing about e to the x and kind of sort of the whole point of it. It's a function who's its own derivative. So what does that mean for antiderivatives? Well, if I go backwards, I also just come back to itself. It's its own antiderivative as well. So e to the x is a function whose derivative is e to the x. But I'm asking for the antiderivative. So that's really just like a pedantic way for me to ask you to write plus c as well. So, right, e to the x plus 1 is an antiderivative of e to the x. E to the x plus 2 is an antiderivative of e to the x. But instead of writing like an infinite number of things, I just write this for short. E to the x plus some constant c, or plus any constant c, is the antiderivative. So it's like a set of functions. A list, kind of an infinite list of functions. Okay, same story for this one. Secant squared. I have to know sort of what like the basic antiderivative of secant squared is. It's tangent, right? And again, that's kind of, you just sort of have to know it, but one of our derivative rules is that tangent's derivative is secant squared. So if I see secant squared, I know it came from tangent. So the antiderivative, so an antiderivative of secant squared is tangent. But I can write plus c to be the antiderivative. So again, sort of, instead of writing like tan x plus 1, tan x plus 2, tan x plus 3, I just write tan x plus c. Okay, so last section here I want to talk about. Why care about antiderivatives? So I spent like 45 minutes talking to you about antiderivatives without really telling you why we would care. So there's good reasons to care. The main reason, I would say, one of the most important reasons, is motion, because we know about what derivatives have to do with motion, right? So you might remember this from 251. If we think about position, velocity, and acceleration of an object. So let's just kind of go over here for a second. An object has a position, and I might use a position function for that. So like, for example, the position, and actually this is a little confusing, but in physics it's really common to use s for position. I might have the position of the function as a function of time. So for example, s of t could be like t squared plus 1 or something. That means that the position of my object is given at every point in time by t squared plus 1. So t represents like what time it is, and this is like a physics experiment, like a ball is falling or something, and I'm modeling the situation with this function. T squared plus 1 is like a parabola, so it looks something like this. So, if I have a physical situation where something is moving in this kind of way, I might use a function to model its motion. S of 0 means like t equals 0, so time 0, so like at the beginning of the experiment. My position is 1, that's just plugging 0 into the function. Then maybe, after 10 seconds, I check what the position is, and it's apparently 10 squared plus 1, which is 100 plus 1. So I have, a position which depends on time. At the beginning, it's position 1. At time 10, it's position 101. And I could check other times based on this function. So my object might have a position function. Something we learned from 251 is that I can actually take the derivative of position, and I'm going to get velocity. So I might say s prime of t if you want, but people usually write v for velocity. And the velocity is like the speed, right? How fast it's going, and also what direction it's going. In this example, my velocity is the derivative of my position. So I can just do the derivative. It's 2t plus 0, so 2t. So that tells me my velocity at different points, right? I can say, well, what's the velocity at time 0? According to the formula, it's 0. So at the beginning, I'm not really moving very much. But then, after 10 seconds, right? After 10 seconds, I know my position happens to be 101. But I'd like to know how fast I'm going. Apparently, I'm going 20. Right, and I really should be saying units. Like, if my original, like t is probably in seconds, right? It could be like in hours, if you want to, just depending on the problem. But it's probably seconds. And the position is probably in like meters or something. So after 10 seconds, I'm at 100 meters. After 0 seconds, I'm at 1 meter. And then that tells me like the units of my velocity too. At time 0 seconds, I'm at 0 meters per second. That's speed, right? And then at time 10, I happen to be at 20 meters per second. If it's not an explicit story problem, I'm often just going to say the number and not the units. But it's usually not that big of a deal. Okay, and so, you can think about this velocity function, right? It's 2t, so it starts at 0 and it gets larger. Maybe my experiment also goes to negative time, so like at negative 1 seconds, my speed would be negative 2, and that may or may not make sense depending on the story problem, but you could plug it in at least. Okay, so there's a relationship between position and velocity, and it turns out it's just based on the derivative. And we drew some pictures like with slopes and stuff, but we didn't know how to do this. Position goes to velocity. You might remember there's one more step, right? I can take the derivative again of velocity. By the way, I'll put some units here. Position maybe is meters, velocity is meters per second. And the derivative is like rate of change, right? Like kind of change in position per time, so it makes sense to become a velocity. If I do the derivative again, you can probably guess, we'll get acceleration. Right, so velocity is the change in position, meters per second. Acceleration is the change in velocity, so meters per second, right? How many meters per second do I gain? And I usually write that as meters per second squared, like meters per second. Like you can imagine there's another like s on the bottom. And I could write s prime prime, or I could write v prime, right? But also I'll probably write a of t for acceleration. Maybe equals. Okay, so in our example, let's have acceleration. It's the derivative of velocity. Our velocity was 2t, so the derivative of that is just 2. And this is kind of interesting. It's a constant function, right? No matter what time it is, at time 100 seconds, my acceleration is still 2. So my acceleration is constant. I'm always accelerating with 2 meters per second. So every second, my velocity increases by 2, which is, by the way, another way of saying what this says. Every second, I go up by 2. And that leads to like a position function, which kind of looks like this. So we have this whole story about position goes to velocity goes to acceleration. We're using derivatives the whole time. So if I know my position function, I can learn about the velocity of my object and the acceleration of my object. What's cool about antiderivatives is we can start going backwards here, right? Now, if I start with information about my acceleration, I can actually use antiderivatives to go backwards and learn about my velocity. Once I have my velocity, I can actually do an antiderivative again to go backwards and learn about my position. So this happens a lot of times in physics, right? You learn about like acceleration from gravity. I could just start by knowing my object falls with a certain constant acceleration due to gravity, and then I can kind of go backwards and figure out like what its position function must be. I'm pretty sure this example is actually kind of about doing that. Okay, so yeah, in this example we have, it's not gravity, but it's the same idea. Yeah, so we'll talk more about this as we go, but generally, like, derivatives are about rates of change, and antiderivatives are kind of about seeing what like the total change is. So we'll see this a lot more, but like if I know enough about my velocity, like over a certain period of time, I can figure out what my position was by kind of going backwards, right? If I know I'm going 60 miles an hour the whole time, then if I go for 10 hours, I can figure out how far I went. So we'll flesh that out a bit more, but going from information about velocity back up to position, or from acceleration back up to velocity, and kind of going both ways down this chain is a lot of the point of this class and why we might care. So let's take a look at this example just in a little bit of detail. So suppose an object has the following function describing its acceleration. Okay, again, so we're starting with information only about the acceleration of the object. I don't know its position function. It's accelerating with this weird function, sine of t plus t squared. It's a little weird, but don't worry about it. It just means, at time 10, I'm accelerating apparently with a force of sine of 10 plus 100, whatever that is. But we can work with it, right? We can do algebra. So I'm starting with the acceleration function. I know suppose we know the initial velocity is 1 meter per second, and its initial position is 0 meters. They're asking what's the velocity after 3 seconds and what's the position after 3 seconds. So we will see that in general, if I'm trying to do this process of going backwards from acceleration up to velocity and then up to position, I'm actually going to need a little bit of data about the velocity and position. That's this initial velocity, initial position. So let's write these down. So what do I know about A? A of t is sine t plus t squared. I know some stuff about the velocity, right? There's going to be some velocity function. I don't know what it is yet. And there's going to be some position function. I don't know what it is yet. But I do know something about them, right? I know that the initial velocity is 1. So whenever we say initial, that's going to mean time 0. You can just translate that in your head to time 0. So that's telling me that at time 0, the velocity of 0, right? Velocity at time 0 is what that means, is 1. So that's like a piece of data that I have sort of written down. I don't know the entire function, but I know its value at 0. Same for position. I know the position when time is 0. It's apparently 0 meters. Okay. Our goal here is going to be velocity at 3 seconds. And actually, we're gonna find this first. Just in general, we're gonna find the entire velocity function, and similarly, we're gonna find the entire position function, and that'll let us answer these questions. What's the velocity at time 3, and in fact, the velocity at any time. Okay. So how can we do this? Well, we can go backwards, right? We had this picture before where position, its derivative is velocity, and its derivative is acceleration. So if I want to start with acceleration and go backwards, I need an antiderivative. And I will use another antiderivative to go all the way back to position. So I just need to find an antiderivative of acceleration. The velocity will be an antiderivative of acceleration. So we can just kind of write it down using the antiderivative rules that we learned before, right? What's the antiderivative of sine? Well, I know that sine goes to cosine, when I take the derivative. I know that cosine goes to negative sine when I take the derivative. I know that negative cosine goes to sine when I take the derivative. So I'm going to come up with negative cosine of t. So again, you can double check the trig rules if you forget exactly how this works, but you just got to check the derivative works, right? I know cosine goes to negative sine, so negative cosine will go to positive sine. So so negative cosine is the antiderivative of sine. You can always check your antiderivative by just taking the derivative and making sure you got what you started with. For t squared, we need my power rule, so it's going to be 2 goes to 2 plus 1, which is 3, and divided by 3, which is the new number. Okay, so that's my velocity function. So that's like, remember, so that's an antiderivative, but when we're doing this, we want to have our plus c, because I want to find all the antiderivatives at once. To figure out what c is supposed to be, right, this is, in this problem, c should be something specific, right? I know the acceleration. Just from this acceleration answer data, I get that the velocity has to be sort of like of this form, something like this, but I don't know just from the acceleration data what c has to be. But it's like a real physical story, and this shouldn't be just like an abstract collection of functions. This should be a very specific function. C should be a specific number. That's where this initial data about the velocity is coming in, right? If I know the acceleration, right, that's like telling me how the velocity is changing all the time. But I got to know like where the velocity starts in order to know the function describing the velocity. Right, acceleration tells me how the velocity changes, which only tells me that the velocity like works this way, but maybe up to a constant. Knowing what the velocity actually starts at, and so it can build off that, is going to tell me what the actual velocity function is. This is actually super easy. We just have to plug this in to here. C is like an unknown that we're going to solve for. Remember, t is the input, so I'm going to have 0 plugged in for t. And the output is 1, right? So like I can even sort of like expand, right? I can write v of 0 as 1. Well, what's v of 0? V of 0 means I plug 0 into all this. So it's negative cosine of 0 plus 0 cubed over 3 plus c. That's like the left-hand side. And that's supposed to be equal to 1. That's like the right-hand side. So I'm just kind of expanding this left-hand side here by plugging in 0. This lets me solve for c, because there's all numbers here except for c. I have to remember what cosine of 0 is. So cosine of 0, just quick reminder, cosine and sine are telling you about the x and y coordinates on your unit circle. So when my angle is 0, I'm right here, right? And cosine is the x coordinate. So the x coordinate is 1 right there. Sine of 0 would be 0, because the y coordinate is 0 right there. Okay, so cosine of 0 is 1, so I have negative 1. 0 cubed over 3, that's 0. And then plus c. So I have negative 1 plus c is 1. And that's enough information to tell me c. I can add 1 to both sides. C has to be 2. So, right, if we had a different initial velocity, we'd have a different c here. So that kind of sets like the starting point for the velocity, but then the acceleration part like kind of tells you how the velocity is changing after that point. So we can write down like a final velocity function. Negative cosine t, I'm just copying, plus t cubed over 3. But then instead of plus c, I know it's actually 2 here, so plus 2. That's enough already to answer our question here. What's our velocity after 3 seconds? Right? I just have to plug 3 in. So it'll be negative cosine of 3 plus 3 cubed over 3 plus 2. And I won't get a final answer, but, you know, plug that into your calculator. It'll be some decimal something. I mean, you can do this part. It'll be like 11, I think. But then this cosine thing is just going to be some decimal. So that's totally a calculator thing. But it's some number. Okay, so we're almost done. Let's just look at this, what happens to the position really quick, and then we'll be done with today's lecture. So we have the velocity function now, right? That was kind of our goal here. We started with the acceleration and we went back to velocity using antiderivative. So we want to start with where we have velocity now. We can take the antiderivative again to go back to position. So let's do the antiderivative of this velocity guy. And again, we can just kind of write it down using the antiderivative rules we learned. Cosine. So I remember that the derivative of sine is cosine, which means this should be negative sine. Right, again, just double check. Right, derivative of sine is cosine, but the negative 1 stays, so it becomes negative cosine. Right, and that matches what we have in the velocity. T cubed over 3. Remember, if I like, I can keep the over 3 is the same as 1/3 out front. Right, so 1/3 t to the 3. This is the same thing. So I can just keep the 1/3 and then do the antiderivative power rule thing to t cubed. Remember, that's plus 1 to the exponent. So t to the 4 over 4. And I'll probably combine those to 1/12 in a second, but I'll just leave it there. And then this is a little bit tricky, right? 2. What's the antiderivative of 2? Well, it's going to be 2x. Right, we talked about like how the derivative of x is 1, right? And if I had a number out front, like 2 times x, its derivative would be 2 times whatever the derivative of x is. So that's that constant multiple rule again. So the derivative of x is 1. So this is 2. So the derivative of 2x is 2. So how to go backwards? Well, 2's antiderivative is 2x. Just as a general rule, if I have 10, its antiderivative is going to be 10x. So you basically just add another x. 7's antiderivative is 7x. Yeah, you're kind of adding another x, right? Like when I do x squared, its antiderivative is x cubed over 3. So I'm kind of adding another copy of x, but then sort of dividing. Same thing sort of happening here. When I go from 10 to 10x, I'm sort of multiplying by another copy of x. And maybe, if you imagine dividing by the exponent, which is 1, and that sort of doesn't do anything. Okay, so we got 2x here, and then just like before, I have to add plus c, because it's just it's the antiderivative of the whole thing. Right, just kind of same logic as before. If I know the velocity function, that tells me how the velocity, just what the velocity is at every second, which is telling me what's the change in position at every second. So I have information about the change of the position, but I don't know what sort of the actual position is unless I know where it starts. I have to know where it starts plus how it changes in order to know the complete story about position. So this plus c is the story of how the position sort of is moving from a starting point, but I need to plug in the starting point. So again, that's our initial position that the story gave us. The initial position was 0. So again, I'll just kind of plug this in. Right, s of 0 is supposed to be equal to 0. What's s of 0? What's this left-hand side? Well, that means I just plug 0 into everything. So I'm just kind of expanding the left-hand side. Becomes negative sine of 0 plus, so this is 1/12 0 to the 4, but I know that's all going to be 0, right? And 2 times 0, that's just 0. Oh, sorry, this is confusing. I wrote 2x here because I was thinking about the this over here, the antiderivatives with x's. This is actually going to be 2t. Sorry about that. That's a very easy mistake to make. I even made it. Remember, this is a function of t. So whenever I do an antiderivative, it's always with t. Right? 2x, right? Its derivative is 2, but like, I need to have a function of time here. So it's really just what's the name of your variable. Here in this problem, the name of my variable is t. So whenever I'm doing antiderivatives, like t is what's going to be involved. I just wrote x sort of on accident because it's really common to do x, right? But in this problem, we're using t's. So sorry if that was confusing. This is actually just 2t. It's not going to change our story here. It's still going to be 0 because I'm plugging in t as 0. But remember, this is like t equals 0, right? So if this was 2x, that like wouldn't make sense. Like I couldn't plug in t equals 0 to x because x is not t. Okay, anyway, so we get 0 here. And then we still have plus c. That's our constant. So that's like expanding the left side of this, plugging in 0. Remember, that's supposed to equal 0 on the right side. So I get to write equals 0. And then I can solve for t in a second. Let's think about this. What's sine of 0? We did talk about this earlier. Remember, sine is the y-coordinate of my point. So when the angle is 0, that's right here. The y-coordinate is 0 right there. So this is 0. So this is kind of nice. We have 0 plus 0 plus 0 plus c is equal to 0. In other words, c is equal to 0. So, it's kind of underwhelming because we did a lot of work and then c just was 0, but that happens sometimes. It's pretty common when the initial position is 0 for c to end up being 0. Okay, so we have like our final position function. So this is kind of cool, right? We started basically just with information about the acceleration and just a little bit of information about the starting position and the starting velocity. And that was like enough information to get the entire position function. So you can kind of think of this as like if I know imagine I know I start right here, and I know I have like an initial velocity that's like I'm going this way with a certain speed. Then knowing the acceleration function is like enough to like recover the exact like position function is kind of what's going on. So we'll talk more about that sort of story, but that's something you can think about. Okay, so let's just cap this off. We were supposed to figure out s of 3. So again, just like before, I can find my position after 3 seconds. That just means plugging in 3 everywhere. And again, I won't really calculate it because it's just a number. But you can, figure it out with a calculator if you need to. Okay, so that was kind of a lot, but that was our first things we're talking about. What are antiderivatives? Why would we care? A lot of story problems are going to be thinking about rates of change. Right, I should say, like, it's not just physics. This story with position, velocity, and acceleration is a really good one, like kind of a basic example to have in your brain. But whenever there's like a quantity that has a rate of change, I can think about going from the quantity to its rate of change with a derivative, and I can think about going backwards with an antiderivative. So it's a very natural thing to want to be able to go both ways, relating a quantity to the rate of change of the quantity. Yeah, so we talked about that, why we would care. We talked about the basic idea of an antiderivative. We talked about the plus c thing. It's important to always remember to do plus c. That'll become more important as we go along. A lot of times it's actually, the plus c is just sort of a placeholder for before you've plugging in the initial conditions. But it'll matter more sometimes. And we kind of reviewed a bunch of basic derivative rules that we should know. And we'll have lots of chances to review all this stuff. So something you should, important takeaway, I think, easy to forget. This kind of stuff I was talking about like the square root being to the 1/2 and the like to the -2 being 1 over x squared, the -1 being 1 over x. That's like super important. Like it's kind of just details, but like it's much easier to do the antiderivatives if you remember those rules. So definitely take a look at those and make sure that makes sense. Cool. So that's the main story for 4.1 here. Next time we'll talk a little bit about 4.2, talking about Riemann sums. So we'll get there. Basically, we're going to be learning about rate of change of a quantity connected to the total change of the quantity. So that's kind of related to our physics story that we were just talking about. So yeah, let me know if you have any questions. Thanks for watching the first lecture, and I will have more of these as we go.